All right, good afternoon, everybody. Welcome to the MATH152 Section 4 SI review session. Your professor is Ellis. I am your SI, Jack Quirk, and today we're going to be looking at examples of basic differential equations. Nothing like you'd see in those higher level courses here, just some basic first order differential equations, things like population modeling, that sort of thing. So, a big part of the differential equations you'll cover in this class is population modeling. We learned that earlier on, the change in population with respect to the change in time was equal to some constant, k times our population function in terms of t. Now, in this particular section, we learned that there's a caveat to this, covering it, we call this logistic growth, and it basically says that we have 1 minus p over 42, oh, my bad, sorry, 1 minus p over m, where m is equal to the carrying capacity of our population. Now, another thing we'll be dealing with is, not in this particular section, but you'll also see in some cases we have to deal with the spring, motion of a spring, or a mass of a spring, which can be solved with a similar equation, kx over m, where x is the displacement function in terms of t, and m is the mass, k is some constant that we're unsure of. Okay. Now, for the most part, we're just going to be dealing with population in this course. It's just the most easily accessible example. So let's take a look at a particular function, and let's break it down. So for this particular example, we have dp over dt is equal to 1.2p times 1 minus p over 4200. Now, first off, want that 1.2p times 1 minus p over 4200. All right, so now we want to know, given this particular function, where is the population increasing? Basically, we want to know where is dp over dt greater than 0. So, if we look at this function, it's broken down into two factors, 1.2p and 1 p over 4200. So, if we look at 1.2p, p obviously has to be greater than 0 in that instance, but other than that, there's really no constraints on this. So for here, p is greater than 0. Now, our bottom factor here, 1 minus p over 400. Now, for this to be greater than 0, p over 4200 has to be less than 1. This is going to happen where p is less than 4200. So combine these, we can see that this equation, this population rather, will be increasing so long as 0 is less than p is less than 4200. Okay, now you might be saying, well, what about less than equal to, less than equal to? Well, if we let equal to 0, then this factor 1.2p is going to be equal to 0. 0 times anything is just 0. So in this case, 0 is not positive or negative, it's just 0, not increasing. And the same can be said for p equal to 4200. When p is equal to 4200, 4200 over 4200 is 1. 1 minus 1 is 0. 0 times anything is 0. Now, another case we can look at, almost the exact same question, except we want to know where the population is decreasing. Okay, so where is the population decreasing? Well, we can't have p less than 0. P cannot be negative. A negative population doesn't really make any sense. We're trying to model a population here. So if we look at this, the only case where we can have a negative number, because the factor 1.2p can't get us a negative, it just can't. 1.2 is positive, we'd have to multiply it by a negative, and p can't be negative, so that's useless to us. But 1 minus p over 4200. Now, this factor can be negative if, but only if, p is greater than 4200, which turns out to be our answer. And you can see that just by looking at the function. If p is, say, 5,000, 5,000 over 4,200 is going to be greater than 1. 1 minus anything greater than 1 is going to be greater than 1. Well, no, I'm sorry. 1 minus anything greater than 1 is going to be less than 0. And in this case, that'll give us a negative dp over dt, which signifies a decreasing population. Now, the last thing that we need to look at when analyzing these functions are our equilibrium solutions. So we'll call this C. And let's see, what are the equilibrium solutions? Now, believe it or not, we already more or less solved for these in our previous examples. Equilibrium solutions basically are asking you, where is dp over dt equal to 0? Where is the population not changing? Where is the population stable? So obviously p equal to 0 will be one of our solutions, because this would net 1.2 times 0 and 1 minus 0 is equal to 0 times 1 is equal to 0, which is what we're looking for. Now, our other one, which again we've already more or less covered, is p is equal to 4,200. Because looking at our equation, 1.2 times 4,200 is 1 minus 4,200 over 1, or I'm sorry, over 4,200 is equal to 1.2 times 4,200 times 0 is equal to 0. So these 0 and 40 are equilibrium solutions. They represent points where our population will not change. In this case, 0 meaning if the initial population is 0, our population can't grow. And 4,200 meaning if our population is at the carrying capacity, it shouldn't change. So that's a basic overview of our logistic growth equations for population. I'm sure we'll see more of those in class. Next differential equations topic I want to introduce you to is just a basic differential equation. So what we have here, we are given 4y double prime is equal to 25, negative 25 times y. And we are given the equation y is equal to cosine of k times t. And what we want to know is what values of k satisfy this differential equation. What should k equal so y fits this parameter? So if we solve for y prime, we get negative k sine of kt. And if we solve for y double prime, we get negative k squared cosine of kt. Now, why are we solving for these derivatives? Well, they're part of our differential equation. And in order to understand what's going on, what values of k will work for this differential equation, we have to plug things in for y. So we end up with, let's see here, negative 4 k squared cosine of kt is equal to negative 25, well, let's see here, one moment, negative 25, sine, negative cosine, so this is going to be positive, or is it? Okay. Apologies for the mistake when I wrote down our actual problem. So, that explains it. Ooh, sorry about that. K squared. Okay. Yeah, that's negative. And this is positive. Apologies. So our initial differential equation should actually have been equal to y double prime is equal to 25. 2 times these smart boards. There we are. 25 y. So plugging this in, we have a negative k squared cosine kt is equal to negative 25k. Oh, that is one more time. Y double prime is equal to negative, there. Okay. So negative k squared cosine kt is equal to negative 25 cosine kt. Sorry about that. Just a little mix up in my notes here. Okay. So cosine kt both cancel out. Divide them over equal to 1. The negatives cancel out, and we have k squared is equal to 25, or k is equal to plus minus 5. So that's just a basic example of a problem we could do given a differential equation, a parameter. Now, I've got one more thing we can look at. So second, this stuff. Okay. So, last thing we'll be examining is whether or not a given differential equation can fit a parameter. So, we have y double prime plus y to sine x. And we're going to be given four functions, a, b, c, d. And we want to know which of these functions fits the parameters of this differential equation. Our first function, y is equal to sine x. Our second function, y is equal to cosine x. Third function, y is equal to 1x sine x. And our last function, y is equal to -1/x cosine x. So just like before, we have to take our y primes of each of these. In this case, y prime is equal to cosine x. In this case, y prime is equal to negative sine x. In this case, y prime is equal to 1/2 sine x plus 1/2 x cosine x. And in this case, y prime is equal to 1/2 x sine x minus 1/2 cosine of x. And one more, y double prime. In this case, it's equal to negative sine x. In the case of b, y double prime is equal to negative cosine of x. In the case of c, y double prime is equal to 1/2 cosine x minus 1/2 sine x plus 1/2 cosine x. And in our final case, we have y double prime is equal to 1/2 sine x plus 1/2 cosine x plus 1/2 sine of x. All right, so now we just, given these 12 equations, we just plug each set in and see which ones work. So in case of A, we have negative sine x plus a cosine of x is equal to sine x. That's not even close. I'm sorry, a little bit of dyslexia today. Sine x, negative sine x plus sine x is equal to sine x. Now, this is obviously not the case because the left side of our equation is equal to 0, the right side of our equation is equal to sine x. That doesn't work, not a solution. Letter B, we have negative cosine x plus cosine x is equal to sine x. Now again, obviously not the case because it comes out to 0 is equal to sine x, not a solution. Now C, I'm going to get close here. We'll have a 1/2 cosine of x plus a 1/2 cosine of x minus a 1/2 sine of x plus a 1/2 sine of x is equal to sine of x. Now simplify both sides of the equation, negative half sine x, positive half sine x, x sine x. My bad. X. These both cancel, which leaves us with our left side of the equation, cosine of x, and the right side of the equation, sine x. Well, that's not right. Not a solution. Now hopefully D will let us something a little better. We have 1/2 sine of x plus 1/2 x cosine of x plus 1/2 sine of x minus 1/2 x cosine of x is equal to sine of x. Now, just very similar to our last problem, except in this case the cosine, 1/2 x cosine x, negative 1/2 cosine x. These cancel out. 1/2 sine x plus 1/2 sine x, so our left side of the equation, sine x, is equal to our right side of the equation, sine x. So D is a solution. A lot of work, but it's a basic way to examine solutions of differential equations. So that'll be it for today. Hope that clarified a few things for people. And hope to see you next time.